In this video, we're going to take a look at how we can find our voltage equations due to different charge configurations. The first one we're going to look at is how do we deal with the case of having multiple point charges. Well, in the previous video, we came up with this expression for voltage due to one point charge that was located by some position vector r. So we're going to do the same sort of thing that we saw when we were working with electric fields and forces, and that is we're going to use superposition. So we're essentially going to look at the effects of each potential charge separately and then sum the effect to get the overall effect. So it's going to be based on this equation for one point charge, but we're going to have to adjust our Q in case our charge is varying between different point charges, and of course our R vector because we're going to have different distances from our observation point to the various point charges. So let's consider a system that has n point charges. So if we have n point charges and we want to find our potential at some point located by our position vector r. So we want potential at r. Our equation is then going to become V at that point located by our position vector r is equal to, so out front we have these constants, so we just have 1 over 4 pi epsilon naught, so that is not going to be changing. And then we're going to have the sum from k equals 1 to n, so we're covering all n of our point charges in the system. And in that summation, we're going to need charge and distance information. So in the numerator, we just have we have q sub k, which is the point charge, the charge value of the kth point charge. And then in the denominator, we're going to have the distance, so the magnitude of the difference between our distance vector for the point of observation and the distance vector for our kth point charge. And again, we're taking the magnitude so that we get the distance of that. So this is how we would find our potential due to multiple point charges. So now we can ask ourselves, well, how would we deal with continuous charge distributions? So continuous charge distributions. And so what these are essentially our line charges, our surface charges, our volume charges. So we've looked at these before with our electric fields as well. And so the approach is going to be essentially the same here, except instead of doing the various point charges Q, we're going to look at a differential charge, and then we're going to integrate instead of summing. So our general approach is to replace our kth point charge with a differential charge. So if it's a line charge, that's going to be a differential length of the line times the charge density, as an example. So differential charge, and we're now going to integrate instead of summing. Okay, so first let's consider the case of a line charge. So for a line charge, we then have the potential at some point located by position vector r is equal to, and we're still going to have that same constant 1 over 4 pi epsilon naught out front. And then we're going to have a line integral over the line where instead of that charge, point charge in the numerator, we now have some rho L, and that rho L is going to be at some position r prime, and we have dl prime. And our distance here in the denominator is going to be our r prime, our r, which locates the point where we want the position, minus our r prime, and it's the magnitude, so we're saying the distance between that. So remember, in general, our prime notation is for our source point, in this case the line charge, or more specifically the differential length of the line charge, and our unprimed notation, as we see here and here, is for the location of interest, or our observation point. All right, so that would be our general expression for a line charge. So we could do a similar thing for surface and volume charges. So let's just write those out for completeness. So our surface charge, and so let's maybe put a line here so we don't get mixed up. So our surface charge V at some point located by position vector r is equal to 1 divided by 4 pi epsilon naught. Now we have the integral over a surface, and our differential charge is now rho s at some source point located by r prime times ds primed. All right, and then in the denominator, we still have the same distance, so it's r minus rr prime and the magnitude, because ultimately we just want the distance. So then finally for our volume charge, same basic idea, we're just going to have a different differential charge for our volume. So we have the 1 over 4 pi epsilon naught out front, integral over the volume, and now our differential charge is rho v at some arbitrary source point located by r prime, dv prime, and then our distance is the same, so that's still an r minus r prime. So with all of these equations, so our multiple point charges, our line charge, our surface charge, and our volume charge, we're all arbitrarily using infinity as our zero potential reference. So let's just come down here and write that explicitly, so we can say all equations, all of these that we've written here in this video, are using or use infinity as the zero potential reference. And so this is because they were all based off of that equation we had for our single point charge, which, remember, we said let's make one of our points be at infinity and make that our zero potential. So we can choose another point as a reference, and if we do that, we're just going to have to add a constant term. So if another point is chosen as our reference, then we have a constant term representing the voltage at that point. So constant term representing potential at our reference point. Okay? And then another thing to keep in mind is that with all of these equations, we're finding our V from our charge distribution, or sort of where our charges are in space. So we're sort of going all the way back and using Coulomb's law. It's worth keeping in mind that, again, we have several different V equations, and we're going to keep expanding on this over the next few videos. But remember, if our electric field is known, then we have a relatively simple equation where we could say the voltage between 2 points is equal to negative integral from A to B of E dot dl. So if we know the expression for our electric field, then we don't necessarily have to deal with the charges directly, because we've already done that to determine that E equation, so we can just plug into this. So again, it's worth keeping track of all of the options we have available, and depending on what we're looking for in a problem and what information is given to us, there might be one form for our voltage equation that is a lot easier to apply than the others.